Hello and welcome to NPTEL MOOC on Fiber Optic Communication Systems and Techniques. In this module, we will look at the receiver operations, the signal processing operations that we perform in order to mitigate various impairments that the signal as it propagates through the optical fiber communication system will undergo. Now, before doing that one, let us actually look at a way to receive or recover the polarization of the transmitted signal. It is important to recover the polarization because in most optical fiber communications today, we use both the X as well as the Y polarizations in order to transmit information. So, usually what we have is one information source which produces X polarized light, and then you can modulate the data onto this one using an external modulator as in a usual sense, and then combine this one with another laser output which is polarized along the Y direction. Okay. Again, you can impose independent data onto each of those polarization components themselves using whatever the preferred mechanism, and it's not even necessary that both should share the same modulation format. For example, the X polarized light could be QPSK modulated, whereas the Y polarized light could be a simple on off keying modulated. Okay. Although in practice all these considerations depend upon what is the transmission reach and the bandwidth and the data rate that we want to achieve for a given application, it is important to note that with using two polarizations, you can simultaneously transmit information at the two polarizations and thereby doubling the usage of your bandwidth. Okay. So, you combine these two using what is called as a polarization beam combiner and then launch into an optical fiber. An ideal optical fiber which does not have any problems associated with it, that is a fiber which has a uniform cross section, no matter at what point you take the cross section remains the same. The fiber does not have any bends or it does not have any micro bends, that is small corrugations or small changes out there. It does not have any major twists, okay, or anything like that. So, in essence, if you consider an ideal fiber, okay, then the two polarizations actually propagate independently of each other, and at the output they will be received as the two polarizations and there is no crosstalk between the two. Okay. We have already seen that when there is such crosstalk, it leads to what is called as polarization mode dispersion, and there are actually, as we saw, there are more than one types of polarization mode dispersion. But in addition to polarization mode dispersion, you will also have polarization dependent loss. What is this polarization dependent loss? That simply means that if the two polarizations talk to each other, even if they do not have a dispersion, but if they just kind of mix with respect to each other, then the output power in one of the polarizations may be smaller while the other one may be larger. Okay. And whether this is smaller or the other one is larger, or whether the Y polarization is larger, smaller, and in fact how much will be smaller and larger, all these are statistical properties which makes polarization dependent loss something very similar to fading that you would encounter in wireless communication systems. And because of this polarization dependent loss, you are not sure how much to amplify the X polarization and how much to amplify the Y polarization, because these values actually change, which forces you to either track the polarizations, for which you should at least be able to recover the polarization of the signals, measure the intensity, and then use some sort of a feedback system in order to track the polarization dependent loss that you are experiencing as a function of time. Alternatively, you simply assume a worst case scenario and put in an amplifier of sufficient power such that the output would be well beyond what you actually expect. But such an approach would be wasteful of your optical amplifier system. It increases the cost, and it may also lead to additional effects such as nonlinearities and additional amplified spontaneous emission noises. So, the sensible way, although it is more complicated, is to actually keep track of the polarization and then to adjust the optical amplifier gains according to the polarization dependent loss. So, the amplifier's gain will be adjusted in a dynamic manner depending on how much polarization dependent loss is happening at any given time. Okay. But before we can deal with PMD and PDL, and I won't discuss much beyond this simple ideas of PMD and PDL, because we don't have enough time in this course. But the idea is that I should first be able to recover polarization. Only then I'll be able to extract information separately which is coming in on the Y polarization and information which comes from the X polarization. And for that we use what is called as a polarization diversity receiver. Okay. What is a polarization diversity receiver? In simple structure of that one would look something like this. So, this is a signal that is coming in which has both polarizations X and Y, and what we do is that we keep a polarization beam splitter. So, we actually keep a polarization beam splitter and direct the Y component in one of the directions and the X component signal in the other arm. Okay. And once they have been separately identified into X and Y polarizations, what we then do is to actually keep a phase diversity receiver. So, with the phase diversity receiver you will have your local oscillator going in as one of the inputs to the phase diversity receiver, and let us say this oscillator is actually emitting an X polarized light, and then you keep the same polarized light into the phase diversity receiver such that you mix the incoming or separated X polarization with the X polarized local oscillator. But at the same time you also want a Y polarized output. So, for that one what you do is to actually keep a polarizer which will change the polarization from X to Y, and you can do so by various things that we actually talked about, or the birefringent crystals, even if we haven't talked about them, and you can convert one polarization to another polarization and then essentially put one more phase diversity receiver. Usually the signals are modulated with the same format so as to keep the rest of the processing kind of similar. If not, then you will have to deal with the fact that one of them is say QPSK modulated and the other one is say on-off keying modulated. But if you keep both to be the same modulation, then this output that you are going to get will be IX plus JQX, where IX stands for the in phase component of the X polarization. Sorry, this is Y here. So, I have IY plus JQY being the baseband complex sample that I am going to get, because what I would actually do would be to put a analog to digital converter here which would be running at the sample rate, so that I can actually generate the in phase component and the quadrature component at any given sampling time, and then essentially obtain one complex sample for every symbol that I have been transmitting. Okay. So, once these are the samples, these are actually discrete signals or digital signals. So, please keep that in mind. Before the analog to digital converter, you have what is called as a analog signal, because signals are varying continuously in time or continuous time signals. Output of the ADC will be discrete complex samples, and you do the same thing even at the other end. So, you have an ADC running in the X branch as well. Usually these ADCs are synchronized to the same clock source. Okay, so that both are sampled almost at the same time. Okay, and both characteristics of ADCs are also kept nearly identical. For example, if this is a 16-bit ADC, you try to keep this one also a 16-bit ADC, so that the two samples are not really different because of the processing that we have used. Of course, depending on the application you may want to change things, but in general for these high order modulation systems which are very high data rates, you try to keep them to be the same. Okay. So, the output of the X polarized phase diversity branch would be IX plus JQX, which is again a complex sample. You combine these two samples together and then process in a unit called DSP unit. Okay. We are going to study the DSP unit. But what are the things that can go wrong? One, you may have thought that these two are orthogonally polarized X and Y. The information is sitting here in the Y polarization, the information is sitting in the X polarization without talking to each other, but it won't really happen that way. If this channel or the optical fiber were an ideal fiber, then sending something on EX, a pulse, sending another pulse which represents information of course on the Y polarization, the output of this one would also be something like EX at the output, which I will call as L, EY at the output of L, with near identical shapes that you have transmitted. Okay. So, in that case the channel would essentially be the identity matrix, or the fiber would essentially act like an identity matrix, and no polarization crosstalk would occur. Okay. This is for the ideal case, but unfortunately in a real world scenario there will always be some crosstalk, which means this value will be different. Okay, this value will be different. We'll put alpha xx and yy just to be sure, and these cross terms that we have put in, right, these are the cross terms that are going to tell you how much of the x component. We will call this as ax and ay instead of calling them as ex and ey, because these are the time dependent envelopes that we are talking about. So let us not write them in terms of electric field, but write them in terms of amplitudes or the complex envelope. Okay, so these complex envelopes are of course functions of time as well, and the cross terms would essentially mean that the output that you are going to get at L will actually contain part of the signal from x and part of the signal from y, and the magnitude of these cross terms alpha xy and alpha yx, which usually are equal to each other but with a different phase normally, are again statistical parameters. So this matrix that I have written should not be interpreted as a deterministic matrix, but it is actually a random matrix. Okay, that is matrix with parameters. Some of those parameters are essentially going to be random, and you need to actually remove this crosstalk from the two branches. So essentially what we are saying is that some portion of x would leak into the y polarized output and then actually shows up here. Some portion of y would actually leak into the x polarized information and then show up at the output. So the idea would be to take this matrix, which is actually a 2 cross 2 matrix the way I have written, and it is not a diagonal matrix, and to actually make that matrix into a diagonal matrix. Okay, it's not so simple. You need to actually work either in the time domain or in the frequency domain appropriately, and if you choose to work, you will almost always have to treat these terms as functions of time and adjust them using some adaptive mechanisms. Okay, so instead of alpha xx, people also write hxx, hxy, hyx and hyy, with the idea that hxx stands for the x polarized input and a pure x polarized output, the impulse response of the fiber corresponding to that. Similarly, for hyy will be the pure impulse response for the input that has been sent in, which is y polarized, and the output is also y polarized, and of course these are your crosstalk terms that we talked about. And then you can actually adjust these outputs. You can actually look at the samples that you have obtained at the two polarizations. So we have actually written this as Ix plus jqy and Ix plus jqx. So rather than writing that way, we will put a shorthand notation for this. We will call this as Ry and Rx. Ry and Rx correspond to the data that you have received or sampled on the y and x branches of the polarization. Okay, and they will have some component of x and some component of y, and adaptively tuning would allow you to remove that polarization crosstalk. And one such mechanism that we have that we use is called as constant modulus algorithm. Okay, this is motivated for those modulation systems in which the amplitudes actually occur, or the amplitudes in an ideal constellation are going to be constant. So these are actually mostly used for QPSK or M-Array PSK types of modulation systems. They can also be used in some sense for constant, or rather only phase modulation systems, but to extend them to include, say, maybe a simple thing as an additional amplitude factor, right. So now you will have an additional amplitude factor, let us say. So this is an example of a system in which both amplitude is changing. So one amplitude value is this fellow with a radius say r1, and the other one is a radius of r2. We will put the capital R1 and capital R2 here, and R1 and R2 correspond to the amplitudes that we have, and within one amplitude you can use a constant modulus algorithm. That is, the amplitude is going to be constant in a single ring, but unfortunately when you use more than one amplitude, you can't use a constant modulus algorithm, but you have to modify it, called as multi-modulus algorithm. Okay, so this multi-modulus algorithm can be used in order to make this matrix look like a identity matrix, which is a 2 cross 2 identity matrix. So that's all you are actually going to do. So from the big picture point of view, polarization dependent loss and polarization mode dispersion in some sense can be thought of as matrices which couple the x and y polarizations, and all the operations that you are going to perform at the receiver most of the time has to be adaptive, but the goal of those operations at the receiver are to make this matrix go back to a identity matrix. Okay, so by whatever the mechanisms that you can use, your basic idea would be to take a correlated matrix or take a matrix which has non-zero elements along the non-diagonal element or non-diagonal elements, and then you have to make those non-diagonal elements go to 0 as much as possible, okay, while making the matrix essentially look like an identity matrix. You may not exactly achieve the identity matrix, but you can get close to an identity matrix, and how close and in what sense we are talking about close depends on the algorithms that you normally use. Okay. So, this was about polarization recovery. We are going to say a little more about this constant modulus algorithm and multi-modulus algorithm later on, but for now let us assume that I am working with a single carrier, single polarization, that is I have both carrier which is a single carrier, which is anyway what we have been considering, and then I also have a single polarization system. By this I mean that at the input I may have sent information only on one polarization, or I may have sent on both, but I am only interested at the receiver side in the x polarized output. Okay, so I am not interested in the y polarization, so I am interested in the x polarized input, and let us see what kind of things can actually happen here. So, let us say this is the signal that we have received, and then I need to have a local oscillator as well, correct. So, let us say this is my local oscillator, this is the phase diversity receiver. This is a shorthand notation I am using, it is not really a correct notation, but I am using this shorthand notation, and to this I am going to send in. So, let us say this is all x polarized, the output of the local oscillator will have some amplitude of square root PLO, whereas the input that I have used here will have a same polarization which we can either call as ES of t, or we can call this as AS of t, does not matter what we have used. Okay. And this could be, as I told you, could be a QPSK system, it could be a simple on off keying, although not quite popular today. It could also be a 16 QAM system or a 64 QAM system. So, these are higher and higher order modulations, and any of these modulated signals would have traveled through the fiber and reached here. You have a polarization diversity receiver which produces, right, the in phase component and the quadrature component, which you are going to combine into a single unit called, in order to obtain the, let us put this as continuous time signals, but then you are going to combine them into one complex sample by using a ADC. Here you have another ADC. Usually these ADCs have to be lined up. So, the clock of this ADC will be in this manner, and in practice, although we want the clocks to be lined up, we may not actually have a lined up clock. So, this difference that you are actually seeing here is a minute difference called as de-skewing of the clock or skew of the clock, and therefore, you need to de-skew the clock. De-skew means they are not aligned with respect to each other. So, you just have to make them align by going back to each other. So, the timing of these two should essentially be the same. So, the skew in the clock has to be recovered. Moreover, if I am actually going to use another phase diversity receiver for recovering the y polarization, of course, in this case I would have IY and QY, and then I will have to deal with this Q problem actually of two more ADCs. So, you see that there are a lot of ADCs, and all these ADCs should essentially have the same clocking source which has to be distributed. So, there is a master clock which would distribute this clock source into different components out there. So, this is the complex sample that you are going to get after you have sampled them through ADCs, and you need to overcome this skewing problem. There are a lot of algorithms to do that one. One of the algorithms is called as Gram-Schmidt orthogonalization procedure. We are going to talk about a little bit about that one in the few minutes now. So, after we have sampled them, so now what we get is a complex sample. Let me just combine them here right away after multiplying the Q component with J. Of course, in reality I am not going to multiply anything with a complex number. This is just for my intuition. Okay. What I do obtain is a complex number, yes, but that will be represented as two real numbers in the processing unit. Okay, so I anyway, for my convenience and for our consideration, consider this to be a complex simple. Okay, after you have done that one, after you have done this deskewing and allowed the I and Q components to essentially come out, the next thing that you are going to do would be to estimate the frequency offset. There are a lot of methods for estimating the frequency offset. Most of them involve using some sort of an extra information called as a pilot, and then you look for this pilot to do the frequency offset correction. There are two types of frequency offset correction. One is called as the coarse correction and the other one is called as the fine correction. Coarse correction is what you first do. You do the fine correction later on, because the next block that you are going to get after the carrier frequency offset is the phase noise block or the phase block. So let me rewrite them here. I am getting a complex sample from the ADCs. The first thing I am going to do is to put a frequency offset. I may do only coarse here and then leave the finer part to combine. So fine frequency offset plus carrier phase estimation. Now carrier phase estimation or simply phase estimation is an extremely important block in this entire receiver system. So if you can pinpoint the difference between DSP based coherent optical communication systems and the older systems, it is in this particular block, because as I have told you earlier also, if you wanted to have a proper coherent detection, you need to have a local oscillator whose phase is and frequency of course has to match exactly with that of the transmitter, or at least the difference between the two must be a constant. Okay. If it is not constant, then it will rotate the constellation points and make your life very, very hard. The conventional way of doing this matching of the two phases or keeping the track of phase is to use a device called as phase locked loop. Unfortunately, optical phase locked loops are very, very hard to implement, and that is the reason why coherent systems were not really used for quite a long time. Okay, because you could not make realizable optical phase lock loops which could track phases over long distance transmission, and especially when data is also involved, and especially even more especially when this data is actually varying at a very high data rate. Okay, in some in future years maybe someone will actually develop a nice rugged optical phase lock loops, and then we will go back to the analog methods, but for now we are dealing with digital methods in which you are going to look at the samples that you have gotten here. So this is the sample that you have obtained, and using these samples you are going to estimate the phase. Okay, this sample will be a function of the actual symbol that has been transmitted. That symbol itself could be a complex symbol indicating the higher order modulation that we have talked about. It will also be a function of the phase, and in this phase there are two distinct phase components that we want to talk about. One is a phase offset. Okay, this phase offset means that let us say the carrier phase is 45 degrees and constant. It may not be, I am just writing it in that way. Then the phase of the local oscillator may be say 30 degrees. So in this case the phase offset, or what is sometimes called as nominal phase offset, is about 15 degrees. But the phase is not going to be constant in this manner. It is actually going to be varying around this 45 degrees, and similarly the phase noise of the local oscillator will also be varying, or the phase of the oscillator will also be varying. This variation is because, as I have told you, because of the finite line width of the local oscillator as well as the finite line width of the signal lasers. Okay, because of this finite line width which is non-zero, you are going to get these phases which will then impact. So you have to first look at the larger or the phase offset, then correct the phase offset, and after that deal with time varying phase noise. Okay, this phase noise comes mainly from lasers. Okay, the lasers that you have used will introduce this phase noise, and you have to actually overcome or compensate this particular phase noise by first estimating it and then compensating. Of course, the received sample will also be corrupted by noise, correct? Because I would have put before the receiver part, I would have put the front end preamplifier. The amplifier is going to actually amplify, but it will also introduce noise into the system, and that noise will actually show up at the sampled output. Okay, I am assuming that the deskewing has been done. I and Q outputs are actually nicely orthogonalized using that Gram-Schmidt orthogonalization procedure that I talked about. I will also talk about it in the next module. because we don't really have time in this one. But then after performing the coarse frequency offset, fine frequency offset, then performing the large phase offset or estimating and compensating for the large phase offset, then you come to laser phase noise. Okay. Luckily for us, laser phase noise is reasonably well defined as a Gaussian process with a variance which has a zero mean, but a variance which is given by 2 pi delta nu divided by r, okay, where r happens to be the symbol rate of the transmitter system. Okay. Delta nu happens to be the line width. When you have delta nu LO and delta nu S, then you can define an effective line width, which usually is the case of something like 1 by delta nu LO by 1 by delta nu S 1 over the entire thing. Okay. Or if the local oscillator line width can be negligible, then you can write down this delta effective mainly in terms of delta nu S. So, one of them is usually the dominant process, okay, dominant line width. And it is interesting to note that the variance of this phase noise is actually inversely proportional to R, which means phase noise for a 10 Gbps system, okay, phase noise which I have written it as Pn for a 10 Gbps system is actually going to be higher than the phase noise for a 100 Gbps system. This is surprising, but the root for this difference actually lies in the way the phase itself goes. If you look at the phase trajectory of a laser, so this is the phase and this is with respect to time, the phase trajectory of a laser exhibits some dependence in this form, but then R corresponds to 2 instants in time, or this is the phase noise, which is actually the phase difference is what we are actually looking for. So, you can in fact model this phase noise as phi k equals phi k minus 1 plus delta theta k, where delta theta k is Gaussian distributed with this particular variance, and k and k minus 1 are the 2 instants that we have looked at. So, k minus 1 and this instant is k. So, the smaller the separation, the larger is the data rate, and therefore, the phase will be more or less same as the previous phase. So, the smaller time separation, larger symbol rate means the variance of the phase noise actually reduces. Okay. So, that is the reason why phase noise for 10 Gbps is actually higher than phase noise for 100 Gbps. So, after you have estimated this phase noise which is time varying, so clearly you would need some sort of an adaptive system to track something that is time varying. Then, and so now you have performed the synchronization, as we would call it, both frequency offset estimation and phase noise estimation would be performed. Now, I am sorry, I forgot to mention one important topic before we go to the frequency offset, and that is dispersion compensation. The fiber would have introduced a lot of dispersion, and then you have to compensate for the dispersion. After compensating for dispersion, which we are going to talk about it in the next module, you do the coarse frequency offset correction, then fine frequency offset plus carrier phase offset plus the time varying phase noise, all of them go into the same terminology called as carrier phase estimation. Then comes an extremely important topic called as nonlinearity mitigation. Okay. Nonlinearity mitigation mainly deals with overcoming the nonlinear effects of which nonlinear phase noise, which is a form of a phase noise, is very important. So, I will tell you more about NLPN in the next modules. After you have estimated and compensated for all these impairments, then you make a decision about the actual transmitted symbol, and this decision could still be in error. Therefore, you characterize the entire system in terms of its BER performance. We are going to see some of these algorithms in the next module. Thank you very much.